Welcome to Quantum Light. This series starts with plain quantum mechanics and builds toward photonic quantum computing, one picture at a time, with experiments you can imagine on a tabletop. Start with something familiar. A classical bit is like a light switch. Off is 0, on is 1. It is always one or the other, never both. A qubit is different. In principle, a quantum system can sit in infinitely many configurations. To build a computer, we pick just two reference states and call them ket0 and ket1, written 0 and 1. Here's the twist. A qubit can be partly 0 and partly 1 at the same time. That combined state is called superposition. To keep track of a qubit, physicists use a picture called the Bloch sphere. Think of an arrow stuck inside a ball. Point the arrow at the North Pole, that is 0. Point it at the South Pole, that is 1. When the arrow lies on the equator, the qubit is in an equal superposition, plus on the right, minus on the left. Where the arrow points tells you the state. Superposition means the arrow leaves a pole and moves on to the equator. The qubit has amplitude on both 0 and 1 at once. When those amplitudes are equal, we write 1 over square root of 2 in front of each. That is a precise balance, not randomness. To get a probability, square the amplitude. Equal amplitudes mean 50-50 odds of measuring 0 or 1, and the squares add up to 1. How do we put a qubit into that balanced superposition on purpose? The simplest gate is the Hadamard gate, written H. A definite 0 goes in, an equal superposition comes out, 50-50 amplitudes, precisely controlled. It can look like a coin toss because measuring gives 0 or 1 with equal odds. But a coin flip forgets its outcome. You cannot undo it perfectly. Hadamard keeps the amplitudes coherent. Their phase stays locked. That is why applying H twice brings you back to 0 every time. 50-50 odds, yes, but coherent, reversible, and ready for interference. Here is exactly what H does to the two basis states. Apply H to 0 and you get plus, an equal blend of 0 and 1 with a plus sign between them. Apply H to 1 and you get minus, the same blend but with a minus sign on the 1 piece. That minus sign is phase. It does not change a 50-50 measurement today, but it will matter when paths recombine. The plus and minus states are both on the equator, so both look like 50-50 if you measure 0 versus 1 directly. But they are not the same state. Plus has a plus sign between its pieces. Minus has a minus sign. That sign is phase, hidden from this measurement, but decisive when two paths meet and interfere. A normal measurement asks a yes or no question. Are you 0 or 1? That is the z basis. Hadamard lets us swap the question. Are you plus or minus? That is the x basis. H is the bridge. It translates between the two ways of asking. Hadamard is not a coin flip. If you apply H twice to 0, you return to 0 with certainty, every time. A coin toss cannot be undone that perfectly. That is because H creates coherent superposition. The phase information is preserved, not thrown away. Here is why phase matters. When two paths recombine, pieces with opposite signs cancel, like water waves that meet out of step. Pieces with the same sign reinforce. In our example, the 1 terms carry opposite signs and cancel. The 0 terms match and survive. Wrong outputs disappear. Right outputs remain. Photons give us a concrete picture. A 50-50 beam splitter acts much like a Hadamard on path states, up to an overall phase. One photon on path A becomes a superposition of path A and path B. Important beginner point. This is not half a photon in each path. It is one photon whose amplitude is split across two paths. Before the full demo, meet the two plates on the bench. A polarizer is a filter. It lets light through in one direction and blocks the other, like horizontal-only sunglasses for light. You can even peel one out of an old LCD computer monitor. A half-wave plate, HWP, is different. It does not filter. It rotates the direction of polarization, like turning a paddle in a stream. Real half-wave plates are special crystals and hard to make at home. For a rough tabletop demo, stretched Scotch tape can act a bit like one. A polarizer prepares clean horizontal or vertical light. A half-wave plate then rotates that clean state. On a tabletop, polarization is the safest way to see this math. Horizontal light H plays the role of 0. Vertical light V plays the role of 1. Remember, a polarizer filters to one direction, a half-wave plate rotates. When you turn the HWP to 22.5 degrees in its mount, it acts like the Hadamard gate. H goes in, and an equal blend of H and V comes out. The third bench piece is a polarizing beam splitter, PBS for short. Unlike a polarizer, it does not block light. Unlike a half-wave plate, it does not rotate polarization. A PBS routes horizontal light one way and vertical light another, splitting a mixed beam into two paths or two bright spots. That is how we read superposition with our eyes. Polarizers are easy at home. Peel one from an LCD monitor. Half-wave plates are harder, though stretched Scotch tape can stand in roughly. A real PBS cube is precision optics. Buy one from a supplier, not something you craft in the kitchen. Setup A is the simplest demo. Light passes through a horizontal polarizer, then the half-wave plate at 22.5 degrees, our Hadamard angle. The PBS splits horizontal and vertical light into separate ports, giving two spots of roughly equal brightness. Setup B adds a second HWP, again at 22.5 degrees. If the first plate had only randomized the light, the second could not undo it, but it does. The beam returns mostly to the horizontal port. Each plate reflects the polarization rather than spinning it, so two of them cancel instead of adding up to a 90-degree turn. The superposition was coherent. Phase information survived the round trip. Setup C is the payoff. A HWP at 0 degrees, its crystal axis aligned differently so it changes only relative phase, sits between two HWPs at 22.5 degrees. The middle plate flips plus to minus. The final HWP turns that hidden phase into vertical polarization, so the beam exits the other port. This is why Hadamard sits at the heart of quantum algorithms. They often hide information in phase, then use interference to turn that phase into a measurable answer. Setup C is the whole story in miniature. A hidden phase becomes a visible output, the same trick behind many quantum speedups. Remember the arc of this video. A qubit can be partly 0 and partly 1. The Hadamard gate places it into a controlled equal superposition, not a coin toss. Phase is preserved, interference uses it, and the same math appears in a simple polarization demo you can build on a table.